Okay, so what I want to do in this session is kind of take you on a bit of a tour of why, and I came about this a little bit by accident more than anything else, in that why bringing IoT security together with AI is actually bringing together two topics that are very important and very relevant to each other. And it all kind of stems from we need to build reliable AI hardware. So with everything that's going on right now in this explosion of AI, a bit like the software-derived vehicles that everybody talks about, it's only ever as good as the hardware that it's built upon. So people don't think too much. You hear all these buzzwords about, AI and LLMs and self-driving vehicles. They're all great software technologies, but they're all reliant on a lot of very, very good, well-built hardware. So if we look at where we are today, I mean, the semiconductor industry as a whole is heading towards this trillion-dollar market, which we're all kind of riding the curve at the moment, and hopefully it's going to continue in the direction that it's going. And I mean, we've seen. I mean, the IoTSF's been around nearly 10 years, and IoT has been a real driver of semiconductor market for quite some time. But I think it's now got to a point where this whole explosion of AI has kind of taken over that mantra, and that's now driving forwards this massive growth in semiconductor technology. And it's not so much necessarily the volume, but the size of the complexity of the AI sort of hardware that we're looking at compared to what we saw with IoT. Because I mean, the story is pretty similar. When we looked at IoT, we were told IoT is going to be everywhere. It's going to be in every single device. It's going to be every single application you've got in the home. So it's out there and it's everywhere. So there's a very similar picture for AI, and it was interesting to see the ARM talk this morning, saying essentially the same thing, in that at some point in the future, we're going to move away from this, keep everything in the data center, to pushing AI and monetizing it kind of on the edge. So I think we're going to see this trend where AI is going to be rolled out to those end applications. So it's not just a kind of a niche technology. It's going to be everywhere. For a lot of us, it's in our daily lives already. But I think it's going to start touching things that we don't even are aware is going to be sat on top of AI. So what's kind of driving the change? So I think things have really moved on from, if we look at data centers, if you look at what people were doing in data centers kind of 5-10 years ago, certainly in the software space that I work in, you would sign up for AWS. You would have some compilation jobs or simulation jobs. You would submit them onto the AWS cloud. They would run for an hour, 2 hours. Job done. But now these vast data centers are being used to train these AI LLMs. And the problem is, and this is where the problem starts to kind of appear, is that when you were running your jobs that were taking 1 or 2 hours, if something happened, well, okay, it crashed or something went down, then I just restart it. If we're training an LLM, that requires hundreds, if not thousands, of GPUs to be running 24/7, consistently, reliably. And if something goes wrong with the hardware, then the whole thing collapses, you have to restart it, and it becomes quite costly, because you might be running a job that's taking say, 10,000 GPUs, 3 weeks, 4 weeks to run. So to restart those jobs now becomes a real issue. So the problem that's hit the guys providing the data center hardware is that the occasional failure was quite acceptable before. Now, having kind of the occasional failure is going to start to cost them big money. And the likes of the Meta world, the Google world, and the Microsoft world, I mean, they all have their own kind of big data centers that are appearing. But they're also they're very aware of the problem, and that's kind of why you're seeing, I mean, if you look back, say, 10 years, did Meta have its own data center? Did Google have its own data center? They were all using kind of off-the-shelf standard hardware, but now they've all got their, I mean, so working in the semiconductor space, we work with all these guys, and they've all built huge teams building their own custom silicon. And part of that is, along with having your own kind of customization, is they want to control the reliability problem. They want to try and be the provider that's up 24/7 for X amount of years without any issues. So there's this big push in terms of reliability that's really driving the technology. And it's also a challenge in the automotive space. So AI is also finding its way into automotive. There's a number of elements of the vehicle today that you're already seeing kind of being taken over by AI. And all of the automotive vendors, both the OEMs and the tier ones, are scrambling to understand how to. I mean, the application of AI is reasonably straightforward, but when you put it in the vehicle, you've got safety and security and all of those things to take into account. So there's a lot of challenges when it comes to putting AI in vehicles. And it's only going to get worse. So, I mean, the guy from ARM today was talking about we're roughly at level 2 plus. As we kind of extend that out to level 3, level 4, the amount of processing on the edge that we need to do, the amount of AI that we're going to see in the vehicle is going to massively increase. So it's a problem that needs to be solved. And in terms of the applications of AI, if we look at some of the features that we're seeing in the vehicles, so I mean, starting with basic kind of lane control, lane awareness, to where these OEMs are working today, where not only are they looking at, oh, look, there's a pedestrian or there's a bicycle or they're actually looking at the movement and the characteristics and the facial expressions to understand, for example, is the pedestrian looking at the car? Did the pedestrian see the car? Or are they looking the other way? So then the car can make a more informed judgment of what to do, because if the pedestrian's looking at the car and has taken them into account, yeah, there's half a chance I'm not going to hit that pedestrian, but if the pedestrian's looking down on his phone, then yeah, I'm definitely going to run them over. So it's so that the application of the AI is getting more and more advanced, and that's driving massively the technology requirements from the semiconductor space, which again, it brings about this reliability problem that we're seeing in the data centers. So it's also there in the automotive space. So it's not a problem that's unique to our high performance compute data center guys. You've got the automotive industry that are driving technology down to these small nodes, 5 nanometer and below, which never has happened in the past because the automotive industry was always focused on nice mature nodes that they understood the life cycle of, they understood the reliability models of, but now to address these technology requirements, they really need to push the envelope in terms of technology. But if we start to look at kind of what an AI device looks like, from our perspective, developing the tools and technology to test them, it's actually quite a nice position to be in, because with all the different AI type devices out there, they tend to follow a pretty standard profile, which consists of a whole bunch of processing elements strung together with some kind of interconnect fabric, and then some kind of high-speed I/O to get the data on and off the chip. But the one thing that has happened, and this is an example of a piece of silicon actually designed and, well, I would say built in the UK, but it was designed and created in the UK by a company down in Bristol called Graphcore. I think this was from about 2 years ago. At the time, it was one of the biggest single pieces of silicon that had ever been made by TSMC, and you can see 23.6 billion transistors. So it had rows and rows of these processing cores, big interconnect exchange in the middle, all the high-speed I/O. And to give you a flavour of how fast this technology is moving, so like I say, I think this was, it was probably roughly about 2 years ago that this device kind of hit the market. And here's another more recent example. This is a chip from AMD, and already you can see there's 153 billion transistors. So it's not a technology area that's standing still. It's moving extremely rapidly. So this whole reliability problem is becoming greater and greater. But like I say, in terms of the physical structure of all these devices, they're all pretty similar, which makes them, for us, it makes them easy to test, because it's just repeatable structures. You can put redundancy in there. So in terms of those type of things, it's quite easy to do. And here's another example. This was an AWS, one of the devices that go into their servers, their data centers. Again, you can see just a massive array of processing cores, all kind of strung together with various redundancy and other activities that are there to kind of help. One of the key things with this example is this was the first piece of silicon that got built with the capability to do full in-system fleet monitoring. So when I say that, people will say, oh, well, actually, don't cars do that already? Don't automotive chips do that already for functional safety? Yes, they do, but it's at a slightly different level. So in a car, you will run certain tests periodically to make sure you meet your functional safety requirements. With this implementation, what the guys at AWS are able to do is basically run the same quality level of testing in field in their data center completely remotely. So they're basically, the process used to be, if there was an issue in the data center, you'd pull the card, you'd get it shipped back to the lab. They might try and take the chip off the board, and if you don't destroy it doing that, you try and put it back on the tester, and it may or may not pass or fail the test. With this, from his armchair, the test engineer can say, well, that looks like that board's not behaving. Just run a complete set of manufacturing tests on that board, and it will report back exactly down to what transistor or what physical feature in the actual chip layout is causing the problem. Maybe there's an open appeared in the metal, or there's a short appeared somewhere, but you can narrow it right down to the physical structure that is failing, which helps in two ways. One, you know that chip's failed, so you can take it out of service, but also you have a database of all the other silicon that sits in that data center, so you can start doing comparisons and say, oh, am I out of time already? So you can start to do kind of really detailed failure analysis and reliability analysis on your data center. And this was a chiplet-based design, and I don't have the actual transistor count, but you can see there was 156 million flip-flops. So these are all massive devices we're talking about. So I saw this popped up on my LinkedIn page just a couple of days ago. So the interesting thing is, with all this hype around IoT and AI, the problem is we still can't beat the god of probability. Statistically, and the chart on the right there comes from the work we do with Meta. When they look at their GPU deployment, they're telling us that as they ramp up to deploying a million GPUs, the probability is that they'll start to see kind of one failure every 30 minutes. So they need to have that unique detection capability so that they can, in an instant, determine what device has failed, take it out of service, apply redundancy, all of those type of things. And even more than that, they want to be able to make sure that we don't wait until the device actually fails. We work on all the data that we've collected about those failed devices so that we can pinpoint exactly when the next one is going to fail and take it out of service before it actually does fail and cause your whole LLM training workload to fall over. So that's quite a scary number, that if you deploy a million GPUs in a data center, you'll roughly see one fall over every 30 minutes. And this was another slide taken from a presentation from Microsoft, actually. So the guy there managing their data center said this technology is crucially important to them because he said, we have this concept of a blast radius. When there's a failure in the data center, whether it's a piece of silicon that's gone down or a cable that's gone down, he said it has such an impact across the whole data center. So he said, we try and deploy as much technology in that data center to reduce the blast radius to an absolute minimum. So if we know exactly down to what transistor has failed in what chip, in what rack, in what section of the data center, we can repair that instantly, as opposed to sending someone in and pulling cables and boards, and could take weeks to correct. And I think the importance of all this technology, we're starting to see. I mean, it was kind of ironic with this coming up that AWS went down beginning of this week. Was it this week or last week? And then I was on a call yesterday, and somebody was giving a demo, and they were logging into their Azure account, and that was down as well. So this is becoming really, really important. So what we're doing at Siemens, so we have basically a strategy and a bunch of technologies that we put sensors and monitors and test infrastructure into the silicon that we can run, as I said with the AWS example, we can run in field, and we can collect all of this reliability data about the silicon. So it's not just a pass-fail testing, we're collecting kind of functional performance data, we're collecting silicon degradation data, temperature, all of those kind of elements. So we can build up, again using AI, we can build up a really nice model which can then do kind of failure prediction. So instead of these data centers having to just continuously replace hardware just in case it's going to fail, we can actually give them predictions on when it's going to fail. So that's kind of the concept about the data center reliability and AI semiconductor reliability. However, it brings a whole new problem, which is very, very relevant to this event, in that we're pulling tons of data off the chip from areas within the chip that are potentially quite sensitive. So we need to secure that chip to make sure that there's no bad actors, or if certain IP providers don't want general access to their diagnosis data, we need to be able to lock things down. So all of the technologies that we've been talking about for the last few years around IoT security apply directly to what we're doing here. So making sure that, because from a functional perspective, you may have security in your device, But if you add this silicon lifecycle management to your device, it's one access element to your device that gives you free access essentially to every single transistor in the device. So it's giving somebody from the outside world access to all the crown jewels. So we need to be locking that down, making sure it's extremely secure. We need to make sure the data coming off the device is encrypted. We need to make sure that if we send any test data to the device, it's genuine and trusted data. So all of the security technologies that we've talked about around IoT security apply directly to this kind of data centers kind of application. So, I mean, like I say, in the interest of time, I won't go into too much detail about what we're doing here, but essentially we have the ability to apply the test data directly from the manufacturing test facility. We have the capability to apply it within the application, so within the data center itself. And then, like I say, the additional element that gives us more information about kind of when the silicon is likely to fail, because regular testing is really just a pass-fail. So it's either working or it's not working. We want to determine kind of when is it going to fail, how is the silicon degrading. So we're adding additional monitoring into the silicon to collect that type of information. So we've got full test infrastructure, we've got full monitoring infrastructure to be able to do that. And like I said, the latest addition to all of this technology is adding that secure element to it to make sure that we can lock down all of that functionality. So that's kind of say an explanation of why IoT security and AI is two important topics that come together. And like I say, the statement there, the secure AI hardware is going to be critical for making sure that you get that trustable AI that you want. Because if your hardware is not secure, then people can mess with your AI, so that your AI is no longer trustable. So there we are. Okay.
Thanks, Lee.
Okay. Any questions?